Seger's Ozone Debugger helps users to quickly analyze and find software bugs that cause CPU faults on the Cortex-M architecture. Let's take a look at Ozone's fault analysis workflow on the basis of a couple of example applications. The example applications can generate different types of Cortex-M faults and can be found on the Seger Wiki. We can download the example applications to a Seger Cortex-M trace reference board. The debug probe in use is a JTrace Pro. Let's advance the first example program execution to function _no_thumb_func. The program counter is on an interworking branch to address 0. Since there is a thumb instruction at address 0, resuming program execution will lead to a Cortex-M CPU fault. Let's resume program execution and see how Ozone handles the fault. Immediately after hitting go, program execution breaks and Ozone's target exception dialog pops up. The target exception dialog shows a description of the CPU fault and its system register context. In this example, the usage fault active flag in the system handler control and state register indicates that a Cortex-M usage fault exception has occurred. The usage fault status register provides the specific type of usage fault exception that has occurred. In this example, the invalid state flag is set, which indicates that an instruction has been executed in an invalid CPU state. The usage fault enable flag indicates that the usage fault handler is enabled. If this was not the case, the exception would have been escalated to a hard fault. Now let's employ Ozone's debug windows to gain further insight into the fault. The call stack window indicates that the target is in usage fault exception state. The window also indicates that the fault originated within function _no_thumb_func. Let's select the call frame of _no_thumb_func within the call stack window. When a call frame is selected within the call stack window, Ozone's call frame aware debug windows will switch output to the execution context of the selected frame. The local data window indicates that an interworking branch to address 0 was performed within function _no_thumb_func. This caused the CPU to execute a thumb instruction in ARM state. Looking into Ozone's register window, the usage fault status register confirms that the CPU has issued an invalid state usage fault. Ozone can also provide accurate information about nested exceptions and nested faults on Cortex-M. To demonstrate this, let's continue debugging the example application. We now overwrite the single branch instruction of the usage fault handler with an undefined instruction. After stepping over the undefined instruction at address hex 8384, Ozone's target exception dialog pops up again as expected. This time, the dialog informs about the Cortex-M hard fault exception, which has preempted the usage fault exception. In addition to the invalid state flag, the undefined instruction flag is now also set. This indicates that both types of usage fault exceptions have now occurred within the call path. The forced flag in the hard fault status register furthermore indicates that the undefined instruction exception has been escalated to a hard fault. As the Cortex-M CPU is now handling a nested exception, Ozone's call stack window has been updated accordingly. Information about nested exceptions can occupy both the main stack and the process stack in the Cortex-M CPU. As the next example demonstrates, Ozone is capable of providing accurate call stack and local data information in this situation. In this example, program execution has been halted at the call stack level 5 on a supervisor call instruction. Following the execution of the supervisor call, an additional function call path has been executed in handler mode. The application now halts on a load instruction that is about to load from invalid address hex 100,000. Also of interest at this point is that Ozone's call stack window indicates that a stack switch has occurred. From the position of stack usage value 0 within table column stack used, users can see that call frames above and including SVC handler are on the main stack. Call frames below and including the SV call exception are on the process stack. 40 bytes of main stack and 88 bytes of process stack are currently in use. Note that Ozone encloses target-specific call frames with angle brackets. Now let's resume program execution to see how Ozone handles the imminent fault. Immediately after program execution is resumed, the target exception dialog pops up to indicate a hard fault exception. The Cortex-M core has escalated the bus fault exception to a hard fault, as the bus fault exception handler was not enabled. The precise error flag indicates that a precise bus fault exception has occurred. The bus fault address register valid flag indicates that the memory access address of the faulting load store instruction is available. Ozone integrates all of this information into the user-friendly exception description shown in the top area of the target exception dialog. The supervisor call active flag furthermore indicates that a supervisor event handler has been preempted for the current exception. Let's close the target exception dialog to further investigate the fault using Ozone's debug windows. As you can see, Ozone's call frame aware debug windows provide a clear picture of the fault. The local data window displays the invalid value of the dereferenced data pointer. The call stack window displays the complete program execution path traced over multiple nested exceptions and CPU stacks. In imprecise fault scenarios, like certain bus faults, the exception might be raised later than the illegal access, usually a few instructions later. In these situations, the Cortex-M core is not able to provide the exact program counter value of the faulting instruction. However, Ozone's trace windows can be employed to quickly identify the faulting instruction. In the scenario shown here, the imprecise bus fault exception can be easily traced back to the faulting store instruction, which is writing to a reserved address, using Ozone's backtrace highlighting feature. This concludes this video on analyzing Cortex-M faults with Ozone. We hope you found it to be informative and helpful. For references, please see the description of this video below. Thanks for watching.